When you close your eyes at night, the stars above seem calm and eternal, but scattered among them are countless silent travelers, drifting in slow arcs across the blackness. We call them asteroids. They are not planets, not comets, but something in between, relics left behind from the birth of our solar system. Some are no larger than a pebble you might kick across a quiet street. Others are massive mountains of stone and iron, drifting alone for billions of years. Tonight, as you rest, let us follow their paths and listen to the quiet story of these wandering rocks of the cosmos, the silent wanderers of space. They move without sound because space carries no air to hold a whisper. Imagine being near one, close enough to see its jagged surface. You would hear nothing, not even the echo of your own breath, just endless quiet, broken only by the distant glimmer of stars. These asteroids travel for millions of years, circling the sun, yet they make no announcement of their journey. Their silence is not emptiness. It is the kind that makes you lean in, as if the universe itself is holding a secret. And though they are silent, their presence is heavy with memory. For every asteroid is a survivor of the early solar system. They are fragments of rock that never became planets, leftovers from the chaos of creation. Imagine a time when dust and gas swirled, colliding, clumping, breaking apart, trying to build worlds. Most of that matter became Mercury, Venus, Earth, and Mars. But some pieces resisted, never merging, never vanishing. They remained as wanderers, scattered, solitary, yet bound forever to the sun. Even in their stillness, asteroids shape stories without words. A small one may streak across the night sky, turning into a fireball as it enters Earth's atmosphere. A larger one might carve a scar into the ground, leaving behind a crater as wide as a city. These are not accidents. They are reminders that silence can also hold power. When something that has floated unnoticed for ages suddenly meets our world, it changes history. It's strange to think how many of these wanderers pass by unnoticed. Astronomers scan the heavens each night, marking their paths, measuring their speeds. Yet most slip quietly through the dark, never seen, never named. We live beneath a sky where countless stones are drifting just beyond our sight. Some so small they would burn away harmlessly, others large enough to alter the course of life itself. The silence of asteroids, then, is not empty quiet. It is a presence, patient and waiting. And when you close your eyes, you can almost imagine their shadow passing slowly over you, as if the universe itself is breathing in long, steady rhythms. These are the wanderers, always there, whether we notice them or not. How ancient people first noticed moving stars. Long before telescopes, long before science gave names, people stared at the night sky with nothing but their eyes. They saw patterns, the constellations, the guiding lights. But once in a while they noticed something strange. A star that moved. Not across hours, but across nights. It shifted slightly, defying the stillness of its neighbors. To them this was not just a light, it was a messenger. Ancient astronomers in Babylon, Greece, and China kept careful watch. They mapped the skies with astonishing precision, noticing these wanderers and calling them planet, the wanderers. They didn't yet know about asteroids, but they sensed that not all stars were the same. Some were alive with motion, some broke the eternal order. Imagine the awe, the unease of seeing a tiny point of light disobeying the heavens. Over time, people tied meaning to these shifting stars. In some cultures, they were omens, and in others, gods moving through the night. The Greeks wove them into their mythology, blending science and story until the two became one. People did not just watch the sky, they felt it was speaking directly to them, each moving point carrying a message that could change destiny. These wandering stars became part of calendars, rituals, and predictions. Farmers looked to them to mark seasons. Priests read them as signs from the divine. What we now know as asteroids may have first appeared to them as strange irregularities, sparks of mystery hidden among the predictable. The human heart, curious and cautious, has always leaned toward mystery, and in a way this old awe never left us. Even today, when astronomers announce a new asteroid passing near Earth, headlines fill with words like close approach and mystery rock. We may have science now, but deep inside, we still feel what the ancients felt, that a moving star means something more than just stone. The moment science gave them the name asteroid. It was the early 1800s, and telescopes were finally powerful enough to notice what the naked eye could not. In 1801, the Italian astronomer Giuseppe Piazzi discovered a faint object between Mars and Jupiter. He thought it was a planet and named it Ceres. Soon, more discoveries followed: Pallas, Juno, Vesta. At first, they were called minor planets, but there was a problem. They didn't behave quite like planets. They were too small, too many, scattered across the same region of space. William Herschel, the astronomer who had discovered Uranus, suggested a new word, asteroid, meaning star-like. Through the eyepiece, they looked like points of light, tiny stars, yet their motion revealed their true nature. This was the birth of a new category in the cosmos. The idea that the solar system held not just planets and moons, but countless other bodies orbiting quietly in the dark. At first, it was unsettling. How many were out there? Did they matter? Could they strike Earth? These questions haunted the early 19th century imagination, and they still echo now. As more asteroids were catalogued, astronomers began to see patterns. Most of them clustered between Mars and Jupiter, in what became known as the asteroid belt. Suddenly the solar system seemed more crowded, more alive. It wasn't just a handful of planets circling the Sun. It was a vast, intricate dance of worlds and half-worlds. The naming of asteroids marked a turning point in human perspective. We were no longer looking at a simple model of the universe. Instead, we saw complexity, abundance, and mystery, all drifting silently beyond our reach. That simple word, asteroid, gave shape to a whole new chapter of discovery. The birthplace of most asteroids, the belt between Mars and Jupiter. If you picture the solar system, you might imagine planets spaced apart like pearls on a string, but between Mars and Jupiter lies a broad zone, filled not with one world, but millions of fragments. This is the asteroid belt. It stretches wide, a river of stone and metal circling endlessly around the Sun. The belt is not as crowded as movies sometimes show. You could travel for millions of miles without touching another rock. Yet when seen from above, it is unmistakable, a band of ancient material orbiting in quiet loyalty. These are the building blocks that never formed a planet, leftovers from the Sun's violent youth. Scientists believe that in the early solar system, dust and gas swirled and collided in a frenzy of creation. Planets were born, pulling material together with gravity. But here, near Jupiter, something different happened. The giant planet's powerful gravity disrupted the process, preventing these fragments from merging into a larger world. They remained scattered, caught in a balance between chaos and order. Every asteroid in the belt carries that history in its bones. Some are made of carbon, dark and primitive, unchanged since the solar system's beginning. Others gleam with metals like iron and nickel, shining reminders of what cores of planets might look like. They are pieces of the puzzle, showing us what might have been. When we think of the asteroid belt, it is not just a place of rock, but a frozen memory. It is the scar of a planet that never came to be, a reminder that even the solar system holds unfinished stories. And through these fragments, we glimpse the early fire that forged our home. Why Jupiter's gravity keeps the belt from forming a planet. Jupiter is the giant among giants, so massive that all the other planets together are still less than half its weight. Its gravity is like a great hand stretching across the solar system, shaping the fates of everything nearby. And in the region between Mars and Jupiter, that hand was strong enough to stop a planet from ever being born. The rocks there tried. For millions of years, fragments collided, stuck together, and began to clump. But every time they grew larger, Jupiter's tug would pull them apart, shaking their fragile unions. Its orbit stirred the region into turbulence, scattering bodies before they could unite. The result? A belt of broken dreams, a field of fragments left unformed. Even today, Jupiter continues to guard the belt. Its gravitational resonance creates gaps like missing teeth where asteroids are cleared away. Astronomers call them Kirkwood gaps, zones swept clean by the rhythm of the giant planet's orbit. Like a drummer keeping time, Jupiter's pull shapes the dance of countless smaller bodies. This same force that prevented a planet also protects Earth. Many asteroids that might have strayed inward are deflected by Jupiter, pulled into new paths, or even swallowed whole. In a strange way, the same gravity that destroyed a planet's chance also shields our fragile world. Destruction and protection bound in one giant's embrace. And so, the asteroid belt is forever tied to Jupiter's presence. Without it, perhaps a new planet would sit there now. But with it, we are left with a cosmic museum of fragments, silent, ancient, and endlessly circling, the variety of asteroid shapes across the solar system. When you first imagine an asteroid, you might picture a perfect ball of rock. But the truth is far stranger. Some are potato-shaped, lumpy, and stretched like clay, squeezed in a child's hand. Others are flattened, jagged, or split in half like broken bread. Their shapes are stories carved by billions of collisions, shattering and fusing them in slow motion across eternity. These bodies are not sculpted by gravity the way planets are. Planets are round because their mass pulls them into smooth spheres. Asteroids are too small for that. Their weak gravity cannot erase the scars of violence. Every bump, every ridge is a memory of an impact, a reminder of survival in the harshest neighborhood of the solar system. Some asteroids even resemble bones, dumbbells, or spinning tops. One famous example, Cleopatra, stretches like a giant dog bone across the dark. How does such a shape remain stable, drifting for millions of years? It seems almost playful, as if the universe was sculpting toys in stone and setting them adrift in silence. Yet these shapes also reveal hidden danger. An asteroid shaped like a top may spin faster and faster, threatening to break itself apart. Others, cracked into two halves, are only loosely held together. These are rubble piles, fragile collections of rock, clinging by the faintest touch of gravity. To see one is to realize how delicate even stone can be in space. The beauty of their variety lies in its unpredictability. No two asteroids are the same. Each carries its own silhouette, its own story, carved over eons. And as spacecraft fly past them, sending home photographs, we realize how much imagination we once lacked. The universe has already painted shapes far beyond anything we could invent. Some are mountain-sized, others no bigger than pebbles. Size, too, is a world of extremes. Some asteroids are so vast they could swallow entire cities. Ceres, the largest, stretches nearly 600 miles across, large enough to hold mountains, valleys, even traces of ice. It is almost a world in itself, a relic of what might have been another planet. But at the other end, countless asteroids are smaller than your hand, tiny stones drift quietly in the void, unnoticed, until Earth's gravity pulls them down. They flash across the sky in an instant, burning as meteors, leaving only a streak of memory behind. A cosmic pebble, but one that carries the weight of time itself. Between these two extremes lies every scale imaginable, from house-sized boulders that could flatten a forest if they struck Earth, to hills drifting unseen between planets. The solar system is filled with these silent companions, each obeying the same sun, each carrying its own size and destiny. What surprises us most is how the small ones are just as important as the giants. A pebble-sized asteroid can light up the atmosphere in a blaze, a reminder of the sky's living breath, while the giant ones hold secrets of chemistry and creation, preserving materials unchanged for billions of years. So whether mountain-sized or pebble-small, they share one truth. They are all fragments of a larger story. The solar system is a quilt stitched together by bodies of every size, and each asteroid, no matter how tiny, is one more thread holding the universe's memory together. The rocky, metallic, and carbon-rich families. Not all asteroids are made alike. Some are hard, rocky masses, dense with silicate minerals, the same kind of stuff that builds Earth's crust. Others gleam with metals, iron, nickel, even precious elements like platinum, shining with the promise of treasure hidden in the dark. And then there are the carbon-rich asteroids, dark as coal, ancient and untouched since the first sparks of the solar system. Rocky asteroids are the most common, stony fragments of the solar system's great collisions. They remind us of mountains and deserts, hard surfaces sculpted by impacts and sunlight. These are the silent majority, filling the belt with their rough, familiar presence. Metallic asteroids, rarer, whisper a deeper story. They may be fragments of larger bodies whose outer shells were stripped away, exposing their glowing cores. To look at one is to glimpse what Earth's own iron heart might look like if laid bare. Some scientists dream of mining them, not just for wealth, but to study the very material that forms planetary centers. Then there are the carbon-rich asteroids, primitive and untouched. They are darker than asphalt, absorbing most of the light that touches them. Yet within their dust lie complex organic molecules, hints of the building blocks of life. If we ever wonder where life began, these bodies might hold the first clues, preserved in black stone for billions of years. 3 families, 3 stories, stone, metal, and carbon. Together they weave the history of the solar system. They are like voices from different times, speaking of how worlds form, how they break, and how life itself may have once been seeded by drifting rock. Why some asteroids look dark as coal, others bright as mirrors. When you look at an asteroid through a telescope, some appear almost invisible. They reflect so little light, blending into the blackness like shadows. These are the carbon-rich ones, their surfaces dark and ancient, coated with material that swallows starlight. To see them is to look at the night itself, captured in solid form. Others, by contrast, shine brightly. Metallic asteroids, rich with iron and nickel, reflect sunlight like polished mirrors. From far away, they gleam like stars. These dazzling rocks reveal how composition changes the very personality of an asteroid. The difference between a shadow drifting quietly and a spark catching your eye across space. But brightness also comes from more than just material. Some asteroids are covered in fine dust, scattering sunlight softly, giving them a muted glow. Others are bare rock, their jagged surfaces bouncing light sharply back into the dark. Like faces in a crowd, some are pale, some are dark, and together they create a cosmic mosaic of contrast. For astronomers, brightness is more than beauty. It tells secrets. A dark asteroid might hide carbon compounds. A bright one may hold metals or ice. Each reflection is a clue, a fingerprint of its makeup. Studying that light, we learn what cannot be touched, what lies hidden in their cores. And so when we say an asteroid is bright or dark, we are not just describing color. We are speaking of identity. Every shadow and gleam is a message, a signal carried across millions of miles, whispering what it is made of and what ancient story it still remembers. How sunlight pressure slowly nudges their paths. It sounds impossible, yet it is true. Even light, weightless, silent, has pressure. When sunlight streams across the void, it pushes gently against every surface it touches. Over millions of years, that push changes the course of asteroids, nudging them onto new paths. The effect is so subtle it cannot be felt in a moment. A spacecraft near an asteroid would never notice. But time in space is long, patient. That constant stream of light, particle by particle, adds up. And over centuries, it can shift an asteroid miles off its original course. This gentle force is known as the Yarkovsky effect. It happens because sunlight warms one side of the asteroid. As it rotates, that heat radiates away, giving it a tiny push, like a sigh of warmth in the cold. The asteroid drifts slowly but surely, a cosmic sailboat carried not by wind, but by light itself. For Earth, this is more than a curiosity. It means the paths of near-Earth asteroids are never fully predictable. Gravity alone does not decide their fate. Sunlight, something we feel every day on our skin, also guides the stones of space, shifting them toward or away from our world. It is humbling to think of that the same light which grows our food, warms our mornings and paints sunsets, also moves mountains of stone in the silence of space. Light, the gentlest thing we know, holds the power to change the destiny of worlds. The mysterious role of the Yarkovsky effect. If sunlight alone can nudge an asteroid, then the Yarkovsky effect is its most delicate trick. It begins with warmth. One side of an asteroid absorbs sunlight during its day. Then, as it rotates, that heat radiates back into space like a faint exhale. This release acts as a tiny engine, pushing the asteroid slowly, invisibly, across the centuries. The mystery lies in its patience. You cannot measure it in hours or days. You need decades, even centuries, before you notice the drift. An asteroid may begin a journey slightly off its course, and hundreds of years later, it arrives in a place no one expected, a shift born from nothing more than heat leaving a rock. Astronomers must account for this effect when predicting asteroid paths. It makes the future harder to pin down, like watching a candle flame flicker. Will a near-Earth asteroid come closer than expected? Will it drift away harmlessly? The Yarkovsky effect holds those answers, hidden in the quiet rhythm of sunlight and rotation. It is also deeply personal in a way. The same warmth you feel on your face in the morning is at work, moving mountains in space. The sun's touch is not just light. It is influence, extending far beyond what we see. And so the Yarkovsky effect reminds us that even the gentlest forces, given time, can change the destiny of worlds, not with violence, but with persistence. Asteroids as frozen time capsules of the early solar system. Every asteroid is a survivor, untouched fragments from when the sun itself was young. While planets reshaped themselves with volcanoes, water, and atmospheres, these smaller bodies stayed frozen, unchanged. They are time capsules carrying the chemistry of the solar system's first days. To hold a meteorite in your hand is to cradle billions of years in silence. Inside its minerals lie clues about the dust and gas that first swirled around our newborn star. They are fossils of stone, not of life, but of time itself. Some contain minerals formed in high heat. Others hold ice, preserved from the cold edges of space. Together they tell us about the extremes of our solar nursery: fire and frost, collisions and calm. The universe wrote its story into them, line by line, molecule by molecule. Spacecraft that have touched asteroids have confirmed this. They have found grains of material older than Earth, untouched by the passage of time. To study them is to travel backward without moving, to see the solar system as it was before Earth had oceans or even a sky. Asteroids are not just rocks, they are libraries of cosmic memory, drifting silently, waiting for us to read their pages. Clues they hold about the formation of planets. Imagine trying to understand how a house was built, but only by studying the leftover bricks and timber scattered nearby. That is what asteroids are for planetary science. They are the unused materials of construction, showing us what the planets were made of and what was left behind. Some asteroids are rich in metals, hinting that they were once part of larger bodies that nearly formed into planets. Others hold carbon and water, suggesting they were the couriers that may have brought these essentials to Earth. Each asteroid is a chapter of the planet-making story, preserved in stone. When astronomers analyze their chemistry, they see fingerprints of early processes: the melting and cooling, the fusing and breaking. From these clues, they piece together how Earth, Mars, and the others came to be. It is like listening to a song long after it was played, by studying the vibrations left in the strings. Even their orbits tell a story. They reveal how gravity pulled, pushed, and shaped the early solar system. Without these wandering stones, we would have only guesses. With them, we have evidence carved in the oldest matter we can touch. Asteroids remind us that planets are not accidents. They are the result of countless collisions and unions, a grand experiment written in stone and metal. And the asteroids are the surviving notes from that experiment. The first spacecraft missions to study them up close. For centuries, asteroids were only points of light in telescopes. But in the last few decades, humanity dared to get closer. Spacecraft like Galileo, near Shoemaker, Hayabusa, and OSIRIS-REx turned faint dots into real worlds. They showed us surfaces pitted with craters, ridges, and boulders stacked like forgotten ruins. When near Shoemaker landed on Eros in 2001, it became the first spacecraft to touch an asteroid. It revealed a world unlike any we had imagined, with dust seas and scattered rocks stretching for miles, a place silent yet alive with history. Japan's Hayabusa missions went further, not only visiting but bringing back samples. Tiny grains of dust, yet older than Earth itself, carried home across millions of miles. To hold them in a laboratory was to touch the dawn of the solar system. NASA's OSIRIS-REx followed, dancing carefully around asteroid Bennu, studying its fragile surface before daring to scoop a handful of dust. That dust is now being studied, a gift from a rock that has circled the sun for billions of years. These missions turned mystery into memory. They showed us that asteroids are not just dots in the sky, but landscapes, rugged, ancient, and holding answers we have long sought. How Hayabusa and OSIRIS-REx touched ancient rock. Touching an asteroid is like touching a ghost of creation. The Hayabusa spacecraft descended onto asteroid Itokawa, briefly pressing against its surface, collecting dust that had waited since the beginning of time. Those grains told stories of heat, cold, and chemical reactions that no Earth rock could ever reveal. Its successor, Hayabusa 2, journeyed to Ryugu. There, it not only collected surface dust but fired a projectile to uncover deeper material, untouched by sunlight. What it brought back was darker than coal, rich with carbon and organic molecules, a whisper of life's ingredients frozen in stone. Meanwhile, Osiris Rex danced delicately with Bennu, its arm extended, touching down for only seconds. The moment was violent and gentle all at once. Bennu's surface, softer than sand, swallowed the probe's arm before releasing it with a cloud of dust. That dust, now back on Earth, is already changing what we know about how life's building blocks may have traveled through space. These missions proved something remarkable, that even tiny spacecraft crossing vast distances could reach out and gather whispers from the past. They showed that our curiosity can extend hands across millions of miles and bring back treasures untouched for billions of years. To touch an asteroid is to bridge time. It is to connect our fragile, breathing present with the silent, eternal memory of the universe itself. The surprising discovery of water traces inside. For the longest time, scientists believed asteroids were dry, lifeless rocks. But when spacecraft brought back samples, a quiet surprise awaited. Within the dust, within the minerals, were tiny traces of water locked away. Not pools or streams, but molecules bound to stone. It was enough to shift our understanding forever. These traces suggest that asteroids may have been couriers of water to early Earth. Imagine countless impacts, each bringing droplets hidden in rock. Over millions of years, those droplets could have grown into oceans. The very seas we know today may owe their birth to wandering stones. The water is not free like a river, but bound in minerals. You cannot see it, but under heat it reveals itself. Scientists have heated grains in labs and watched vapor rise, as if the stone itself exhaled. Each puff is a memory of ice preserved from the dawn of the solar system. What is astonishing is how widespread this might be. Not one asteroid, but many seem to carry traces of water. It means the universe hides more resources than we thought, not just rock and metal, but elements of life itself scattered across space. Water, the same element that shapes rivers and rain here, also lingers in silence inside rocks drifting between planets. A reminder that life's ingredients are not bound to Earth alone. They are universal, waiting, hidden, carried by stone couriers of the stars. Organic molecules found deep within their cores. If water was a surprise, then organic molecules were a revelation. These are the basic building blocks of life, carbon chains, simple but essential. And they were found inside asteroids, preserved untouched for billions of years. It was as if the universe had left seeds scattered across the solar system, waiting for fertile soil. These molecules are not alive, not even close, but they are the alphabet of biology. Combine them in the right ways, and they can form amino acids, proteins, the architecture of cells. The fact that asteroids carry them suggests life's recipe was written long before Earth was ready to read it. Scientists found them in samples from Ryugu and Bennu, dark grains that looked ordinary, but under microscopes revealed rich complexity. They were not rare, not exotic. They were common enough to suggest that life's chemistry might be universal, not confined to one fragile world. Imagine the early Earth bombarded by asteroids carrying water and organics, a storm of stone, but also a delivery of possibility. Out of destruction came creation. Our oceans, perhaps, were seeded not just with liquid, but with potential for life itself. It is humbling to think that the same rocks drifting in silence today once carried the whispers of biology and perhaps, without knowing it, delivered the spark that would become us. The possibility that life's seeds traveled on asteroids, this idea has a name: panspermia. The thought that life, or its earliest ingredients, traveled across space on stones and ice. It is not fantasy. We already see the proof in water and organic molecules hidden in asteroids. The seeds are there. The question is whether they ever found fertile ground. Asteroids striking Earth billions of years ago may have carried these seeds. When the planet was still cooling, when oceans were just forming, each impact was a delivery of raw material. Perhaps in the warmth of those waters, chemistry began to stir, and the first whispers of life emerged. The thought stretches further. If Earth could be seeded, could other worlds be as well? Could Mars, Europa, or distant exoplanets have received the same couriers? The universe might not be a desert, but a garden, with asteroids as the gardeners, carrying life's basics wherever gravity pulls them. Skeptics argue it is chance, coincidence that chemistry alone could have created life on Earth. But the presence of these molecules in so many space rocks makes one wonder. Perhaps life is not rare. Perhaps it is inevitable, seeded again and again, waiting for the right place to bloom. And so as you imagine an asteroid drifting quietly, know it may be carrying not just stone, but history. Not just history, but the possibility of life yet unborn, waiting to find its soil somewhere among the stars, the scarred landscapes they leave on Earth's surface. Every time an asteroid meets Earth, it leaves behind a mark, a crater, a wound carved into the planet's skin. Some are shallow and forgotten, hidden by forests and rivers. Others are vast, unforgettable, stretching for miles. They are reminders that the sky is not empty and that Earth has always lived under quiet bombardment. The Arizona meteor crater is one of the most famous, a mile wide, over 500 feet deep, formed in an instant 50,000 years ago. To stand at its edge is to feel the force of a cosmic hammer delivered by a rock no larger than a house. Other scars are older, hidden in geology. Sudbury in Canada, Chicxulub in Mexico, places where impacts reshaped the Earth's destiny. Some brought fire, others oceans. Some even tilted the balance of life itself. Each crater is more than a hole. It is a page in the story of survival and change. Even today, small impacts continue, tiny meteorites striking unnoticed, leaving stones scattered across fields and deserts. They are reminders of the quiet rain of space that still falls, though we rarely notice. The scars on Earth are not just destruction, they are records. They tell us the history of our planet's relationship with the stars, of times when the universe reached down and touched us with stone. How craters became silent storytellers of past impacts. Craters do not speak, but they hold stories. The layers of rock reveal pressure, heat and shock that no other force on Earth can replicate. They are frozen moments of cosmic collision, preserved in stone long after memory has faded. Scientists read them like archaeologists. The minerals formed at impact, the melted glass, the patterns of shattered rock, all are words in a language of violence and survival. They tell when the asteroid struck, how large it was, what direction it came from. A story hidden in silence until uncovered. Some craters are so vast they became lakes, others filled with forests, cities, and life long after their creation. Nature heals, yet the scars remain if you know how to see them. Even beneath oceans, sonar reveals circles deep in the seabed, silent witnesses of past strikes. What makes them haunting is their permanence. Erosion may smooth them, vegetation may hide them, but the Earth never forgets. Each crater is a mark of how fragile life can be, and how resilient it has proven to be. Craters are not just evidence of destruction, they are storytellers, reminders that even in the face of cosmic impact, life continued, adapted, and found new ways to grow. The event that ended the dinosaurs' reign, 66 million years ago, the sky above Earth changed forever. A giant asteroid, nearly 6 miles wide, struck near what is now the Yucatan Peninsula in Mexico. The force released was beyond imagination, more powerful than billions of atomic bombs. In a single moment, life's balance was tipped and the age of dinosaurs came to an end. The asteroid's impact carved a crater more than 90 miles wide. Rock vaporized instantly, oceans boiled, and shockwaves circled the planet. For creatures nearby, it was sudden and final, but the story did not stop there. The real devastation unfolded in the days and years that followed. Dust and ash filled the sky, blocking the sun's warmth. Temperatures plummeted, plants withered, and food chains collapsed. The mighty dinosaurs, rulers for millions of years, could not endure the long winter that followed. Small creatures survived, mammals hiding underground, birds that could adapt, but giants perished under the weight of silence. Scientists call this the Chicxulub impact. It was not just destruction, but transformation. Without it, mammals, and eventually humans, may never have risen to take their place. It was a moment of death that carried the seed of a new beginning. And so one asteroid ended an era and began another, reminding us that even silence from the skies can suddenly roar, rewriting the story of life in an instant. The global fires and darkness that followed. The impact did not end with a crater. When the asteroid struck, fragments of molten rock were hurled into the air, raining down across continents. The atmosphere ignited with heat, and vast forests burned in global wildfires. A world once green and alive became a furnace of flame. Animals that survived the first blast faced a world cloaked in smoke. Sunlight dimmed to twilight, even at noon. For months, perhaps years, the earth lay under a veil of darkness. The warmth of the sun was gone and ecosystems collapsed in silence. In oceans, plankton died as light disappeared. On land, plants shriveled, unable to photosynthesize. The chains of life snapped one by one, leaving only the most adaptable to endure. It was not just the dinosaurs that perished, but countless other species. A mass extinction that reshaped the earth forever. Yet from this darkness, new life slowly began. Small mammals, burrowing birds, and resilient plants found niches in the altered world. Their survival carried the story forward, proving that even after fire and shadow, life finds a way. The global fires and darkness were not just endings. They were the crucible in which the modern world was forged. Through destruction, Earth was remade into a place where new forms of life could thrive. The role of small impacts still shaping Earth today. We often think only of giant impacts, but Earth still meets smaller asteroids regularly. Every year, thousands of tons of space dust and rock fall into our atmosphere. Most burn away harmlessly as meteors, streaks of light across the night sky. Yet some survive, landing as meteorites scattered across deserts, ice fields, or even backyards. These smaller impacts may not end eras, but they shape Earth in quieter ways. A crater the size of a pond here, a new mineral discovery there. Each fragment is a messenger from the solar system, reminding us of our place in the wider cosmos. Even in recent centuries, larger but still modest impacts have been recorded. In 1908, a powerful explosion leveled forests in Tunguska, Siberia, likely caused by an asteroid just a few hundred feet wide. In 2013, a meteor over Chelyabinsk shattered windows and injured over 1,000 people, though no one died. These events remind us that the sky is active, not still. Earth is part of a living system where stones occasionally fall from the heavens. They are warnings, but also gifts, because each impact teaches us more about the nature of these wanderers. From dust to fireballs, small impacts continue the dialogue between Earth and the stars. Quiet reminders that the story of asteroids is not finished, but ongoing, written even now in flashes of light across the sky. Why meteor showers light up our skies each year? There are nights when the sky itself seems to sparkle with falling stars. These are meteor showers, and though they feel magical, their origins are deeply cosmic. They occur when Earth passes through trails of debris left behind by comets and sometimes asteroids. Each tiny fragment burns in the atmosphere, painting the night with fire. Showers like the Perseids in August or the Geminids in December have been watched for centuries. Ancient people saw them as omens, blessings, or messages from the heavens. Today, we see them as beauty. Yet they are also the quiet voice of space reaching us directly. What is most enchanting is their predictability. Every year, at the same time, the Earth returns to the same trail, and the meteors return to the sky. It is like an annual appointment with the cosmos, a reminder of cycles far larger than our own. Each shooting star is no larger than a grain of sand, yet it burns brighter than fireworks as it collides with the air at incredible speed. To think such beauty comes from something so small is a lesson in wonder. Meteor showers show us that not all encounters with asteroids or comets are destructive. Some are simply gifts, a free performance of light, given to anyone who looks up. The difference between meteoroids, meteors, and meteorites, it can be confusing. Meteoroid, meteor, meteorite. But the difference is only a matter of where the stone is in its journey. A meteoroid is a small rock drifting in space, too small to be called an asteroid. When it enters Earth's atmosphere and burns, it becomes a meteor, the streak of light we call a shooting star. If a piece survives the fall and lands on the ground, it is a meteorite. Each stage has its own magic. As a meteoroid, it drifts quietly for ages, unnoticed among billions. As a meteor, it flares briefly, bright and breathtaking. As a meteorite, it becomes something you can hold, a fragment of the cosmos resting in your hand. Meteorites are especially precious. They are time capsules, untouched since the solar system's birth. Some are stony, others metallic, and a few even carry rare minerals not found on Earth. Scientists treasure them for the clues they hold, but collectors and dreamers treasure them for what they are: tangible pieces of the universe. The journey from meteoroid to meteor to meteorite is brief but profound. From drifting unnoticed to blazing in glory to resting silently once more. It is a cycle that mirrors life itself, arrival, transformation, and memory. So when you see a shooting star, remember, it is more than a spark in the sky. It is a traveler, perhaps on the last moment of a journey that began billions of years ago, now writing its final story across our night. How scientists hunt for space rocks on frozen plains. When a meteorite falls to Earth, finding it can be like searching for a needle in a desert of stones. Yet scientists have developed clever ways to hunt them, and one of the best places is on frozen plains, where black space rocks stand out against the endless white. Teams of researchers travel to these regions, scanning the ice on snowmobiles or even on foot. Their eyes trained to spot the slight contrast, a dark fragment lying on the shimmering surface. Each find is tagged, logged, and carefully collected to preserve its story for the lab. The frozen ground is not just convenient, it protects. Meteorites that fall there are less weathered, less altered by rain, soil, or plants. They remain pristine, close to the condition they arrived in from space. That purity is priceless because it means scientists are studying the rock as it was billions of years ago. The excitement of discovery is quiet but profound. Imagine bending down, brushing away snow, and realizing you are holding something that began its journey before Earth even had life. It is like picking up a message written in stone and delivered across the cosmos. These hunts remind us that science is not always in laboratories or observatories. Sometimes it is in frozen silence under an endless sky, with human eyes scanning the horizon for whispers of the universe. Why Antarctica is a treasure chest of meteorites. Antarctica, more than any other place on Earth, holds the greatest collection of meteorites. Not because more fall there, but because the icy surface preserves and reveals them so clearly. Against a landscape of endless white, a black rock stands out like ink on paper. The continent's ice sheets move slowly, carrying fallen meteorites toward ridges where the wind strips away the snow. There they gather in clusters, waiting for scientists to find them. It is as if Antarctica is not only preserving, but also delivering these stones to human hands. Over the decades, expeditions have recovered tens of thousands of meteorites from Antarctica. They include every type: stony, metallic, carbon-rich, even fragments from Mars and the Moon, blasted away by impacts and carried across space before landing on this frozen world. The cold ensures they are remarkably well preserved. Unlike meteorites found in deserts or forests, Antarctic samples show little contamination. They are clean, unspoiled, and ready to tell their stories to researchers. So while Antarctica seems barren, it is in truth a library of cosmic history, a place where the past rains down and waits patiently, preserved by ice and silence, for us to read its secrets. The rare metallic meteorites humans have used for tools, long before people understood astronomy, they already held pieces of the cosmos in their hands. Metallic meteorites, rich in iron and nickel, were sometimes discovered by ancient cultures. Unlike ordinary stone, these metals could be shaped, hammered, and polished. They became tools, weapons, and sacred objects. In Egypt, beads dating back thousands of years were made from meteorite iron. In Inuit traditions, large metallic meteorites were used as a source of material for knives and spear points. These were not just objects of utility, they were revered as gifts fallen from the sky. Metallic meteorites are rare, but their strength and beauty made them stand out. They often gleam with a natural crystalline pattern called the Widmanstätten pattern, a design so intricate it looks as if it was crafted by hand, but it is the slow work of atoms cooling in space over millions of years. For ancient people who had never seen smelted iron, a meteorite was a miracle. It provided a metal harder than anything they could mine, dropped directly at their feet by the heavens. It is little wonder these stones were treated as treasures and woven into legend. To hold one today is to touch what our ancestors once touched, a fragment of space that linked their world with the stars, both useful and sacred at once. Legends of sky iron shaping ancient swords. Stories and myths often grew around these rare gifts from the sky. One of the most famous legends is of weapons forged from sky iron, blades made from meteorites that were said to carry otherworldly power. These tales are scattered across cultures from Asia to the Middle East. In some traditions, swords of sky iron were believed to never break, to cut more cleanly, and to hold a spirit within. The idea of wielding a weapon not born of earth but of the stars gave warriors a sense of divine strength. The cosmos itself seemed to flow through the blade. One such blade is said to have belonged to Tutankhamun, the boy pharaoh of Egypt. Tests on his dagger revealed that the iron did not come from earthly ore, but from a meteorite. Even kings sought the power of the heavens, carrying it into life and death. Such stories remind us how deeply humans have always connected the sky with destiny. To carry a piece of the stars was to carry something beyond human reach. It turned an ordinary object into a symbol of eternity. These myths endure because they carry truth, not just in the existence of meteorite iron, but in the way humans have always sought meaning in the heavens, forging the unknown into tools of survival and story. The gold and platinum hidden inside some asteroids. While many asteroids are rock or carbon, some are treasure chests of metals. Within them lie gold, platinum, and rare elements in concentrations richer than those found on Earth. These metals formed in ancient cosmic furnaces or the supernovae and collisions before being locked into drifting stone. The thought of such riches has fueled dreams of asteroid mining. Imagine spacecraft traveling to these rocks, extracting metals worth trillions, enough to change economies. It sounds like science fiction, yet the technology is already being studied by companies and space agencies. But beyond wealth, these metals tell stories. They reveal the processes that shaped planets, the cores that melted, the fragments that broke away. A metallic asteroid is not just treasure. It is a window into how Earth's own iron heart was formed. Some scientists believe that if we can reach these asteroids, we may gain resources not just for Earth, but for future space exploration, metals that could build stations, fuel technology, and carry humanity further than ever before. Gold and platinum in asteroids remind us of two truths: that the universe holds riches beyond imagination, and that true treasure is not just material. It is knowledge waiting inside every stone drifting in the dark. Why billionaires dream of mining them one day? In recent years, the thought of asteroids has shifted from mystery to opportunity. Not just scientists, but billionaires and companies began imagining them as future mines. Inside certain asteroids lie metals more abundant than all Earth's reserves combined. Gold, platinum, and rare elements essential for technology shimmer quietly in drifting stone. The dream is bold. Spacecraft traveling across millions of miles, landing on rocks with almost no gravity, and extracting treasure in silence. Some imagine robotic miners, others imagine human crews, building the first industries beyond Earth. To the ambitious, asteroids look like vaults floating freely in space. Yet this dream is not only about wealth, it is about freedom. On Earth, resources are limited, bound by politics and geography. In space, asteroids are open, untouched, waiting. To tap them would be to step into a future where humanity is no longer confined to one planet's resources. Of course, it is not simple. The challenges of mining an asteroid are immense, from anchoring on a surface that barely holds you to transporting material back across the void. But in every dreamer's heart, challenges are invitations, not barriers. And so when billionaires look to the stars, they see not only mystery but opportunity. A new gold rush, not in rivers or mountains, but in silent stones drifting between worlds. The challenge of reaching and anchoring on a tiny rock. Asteroids may look solid, but in truth many are fragile. Some are rubble piles, barely held together by gravity, weaker than a whisper. To land on one is like trying to stand on a cloud made of stone. Every step risks floating away. Spacecraft engineers know this well. Anchoring on an asteroid is one of the greatest challenges. You cannot simply land with heavy feet. The craft must cling gently, using harpoons, anchors, or even sticky pads designed for the weightless dust. It is a ballet of precision, not a conquest of force. The difficulty grows when you realize how unpredictable these rocks can be. Their surfaces are uneven, shifting, even hollow beneath the dust. A spacecraft must be ready for surprises, for crumbling ground, for bouncing where it expected to settle. It is exploration on the edge of the unknown. And yet these challenges are part of the beauty. The fragility of asteroids reminds us they are not planets. They are survivors, delicate collections of fragments that have drifted together and held on for billions of years. To touch one is to touch something as fragile as memory itself, The challenge of anchoring, then, is not just technical. It is symbolic, a reminder that the universe is not conquered by force, but by patience, respect, and the gentlest of touches. Gravity so weak, a jump could send you drifting away. On Earth, gravity holds us tight. We leap, we fall, and we return. But on an asteroid, things are different. Gravity there is so faint that a single jump could send you into space, never to return. A frightening thought, but also a glimpse into how fragile these worlds really are. Astronauts on such surfaces would need to tether themselves like climbers scaling invisible cliffs. Every move would be deliberate, every step secured. On an asteroid, freedom of movement becomes a delicate dance where safety is measured in ropes and caution. Even spacecraft must respect this weakness. Engines cannot fire too hard, or they risk pushing the craft back into the void. Landings must be more like gentle touches, almost whispers, careful not to disturb the balance of dust and stone. And yet, this weakness is also opportunity. In such light gravity, moving material is easy. Mining, construction, exploration, all could be done with less effort than on Earth, if only the technology can be mastered. The very danger becomes a gift. To imagine standing on a world where a jump could set you free is to realize how diverse the cosmos truly is. Gravity, the invisible hand that rules Earth, becomes a suggestion here, not a command. How astronauts may one day visit them as stepping stones. Asteroids are not just objects of study or mining. They may one day serve as stepping stones for deeper journeys into space, platforms where astronauts can stop, refuel, or gather resources before venturing to Mars and beyond. In this vision, asteroids are not just rocks. They are ports in the ocean of the cosmos. Visiting them would be different from visiting planets. There are no skies, no seas, no atmospheres, only silence and stars. Yet this silence may be exactly what humanity needs. Practice in surviving far from Earth, in adapting to alien environments. Astronauts could learn to work in microgravity, to harvest materials, to test life support systems. Every visit would prepare us for greater challenges. Each asteroid touched would be another page in humanity's training book for the stars. The thought is humbling. Humanity, still young, learning to walk in space by using ancient rocks as teachers. Our ancestors once used islands across oceans as stepping stones. Now we may use asteroids across the solar system in the same way. One day, when humans stand on Mars or travel to distant worlds, we may look back and remember that the first steps were not on planets, but on small, drifting stones, the quiet companions of our sun, asteroids as fuel stations for deep space travel. There is another vision for asteroids, one even more practical. Within them may lie not just metals, but water ice. And water, split into hydrogen and oxygen, becomes rocket fuel. An asteroid could serve as a refueling station, turning journeys that seem impossible into voyages within reach. Imagine spacecraft leaving Earth heavy with only minimal supplies. They travel light, knowing that along the way, asteroids will provide what they need: fuel for engines, water for crews, oxygen for breathing. Suddenly the solar system feels smaller, friendlier, more connected. This idea is not science fiction alone. NASA and other agencies have already studied how asteroid resources might be used. The technology is not yet ready, but the physics is clear. Asteroids are not just obstacles, they are opportunities waiting to be tapped. In a sense, it would make humanity's expansion sustainable. Instead of carrying everything from Earth, we would use what the cosmos already provides. Each asteroid, then, becomes not just a rock, but a station, a harbor in the endless sea of space. Asteroids as fuel stations transform them from relics of the past into bridges to the future, silent reservoirs that may one day light our engines and carry us farther than we ever dreamed. The silent risk of near-Earth asteroids crossing our orbit. Among the countless stones drifting in space, some share a special relationship with us. They are called near-Earth asteroids, bodies whose paths bring them close to our planet's orbit. Most pass harmlessly, silent companions circling the sun alongside us. But their presence carries a quiet risk. The vast majority are small, burning up harmlessly as meteors, but a few are large enough to cause damage if they ever cross paths with Earth. These are the silent risks, not immediate, not constant, but always possible. They remind us that our skies are not entirely still. Scientists track these objects with great care. Each night, telescopes scan the heavens, mapping their paths, predicting their movements. It is a cosmic watchfulness, a duty to know where each wanderer might travel in years or centuries ahead. Yet the risk is not just in their size, but in their unpredictability. Sunlight can nudge them, gravity can bend them, and what seems safe today could drift into danger tomorrow. The sky is alive with motion, and no orbit is truly eternal. The silent risk of near-Earth asteroids is a humbling truth. We are not only citizens of Earth, but participants in a wider cosmic system where stones from the beginning of time still wander near our fragile home. NASA's watchful eyes scanning the skies every night. To guard against these risks, humanity has turned its eyes upward with discipline. NASA and other agencies run programs dedicated to scanning the sky every night, cataloguing asteroids, and calculating their paths. It is patient work, a nightly ritual of vigilance. Powerful telescopes sweep the heavens, recording faint points of light that move differently from stars. Computers track these motions, comparing them to known objects. When something new appears, it is logged, measured, and studied carefully. Each detection adds to a growing map of the stones circling near Earth. These observations are not just numbers, they are predictions of the future. With careful math, scientists can forecast where an asteroid will be in years or even centuries. Some are marked as harmless, others flagged for further watch. It is like predicting the weather, but for rocks that drift through the solar system. The effort is global. Observatories across continents, radar systems, even amateur astronomers all contribute. Together, they weave a safety net of awareness, watching over the skies so that no surprise comes unnoticed. And in this quiet vigilance lies a kind of comfort. Humanity, once blind to the heavens, now keeps careful watch. We may not control the stones, but we no longer face them in ignorance. How early warning systems calculate their paths. When a new asteroid is discovered, the first step is to measure its orbit. Astronomers take repeated observations, tracing its motion across the stars. With each data point, the picture sharpens, where it came from, how fast it moves, and where it will go. But predicting a path is not simple. Gravity from planets, the tug of the sun, even the subtle push of sunlight must be considered. The calculations grow complex, weaving together forces that play out over years. The result is a projection, a map of possibilities for its future journey. Early warning systems are designed to spot potential threats long before they come close. If an asteroid appears to have even a tiny chance of intersecting Earth, it is flagged, tracked, and watched with extra care. Often, new data narrows the uncertainty, ruling out danger, but sometimes the math shows a possibility that cannot be ignored. It is in these rare cases that humanity considers its options, from monitoring to perhaps one day deflecting. The very act of calculating these paths shows how far we have come. What once was the realm of myth and omen is now measured in numbers, predictions, and quiet preparation. The concept of deflecting an asteroid with gentle nudges. If an asteroid ever truly threatened Earth, the solution would not be to destroy it, but to nudge it gently long before it arrives. A tiny shift in its path years ahead could mean safety when the time comes. One concept is to send a spacecraft to fly alongside the asteroid, using its own gravity to slowly tug the rock into a new orbit. Another is to use solar sails or beams of light to push it ever so slightly, taking advantage of the same forces that naturally nudge them already. Other ideas include impacting the asteroid with a probe, not to shatter it, but to give it a small push. In space, even the smallest change in speed, if applied early, becomes a vast difference over time. These gentle methods remind us that prevention lies not in violence, but in patience and foresight. The universe teaches us that time is the most powerful ally when shaping destiny. To imagine deflecting an asteroid is to imagine guiding a wandering stone with a whisper, not a shout. It is a vision where humanity learns to dance with the cosmos, not fight against it. The historic DART mission testing planetary defense. In 2022, humanity took its first real step toward this vision. NASA launched the DART mission, a spacecraft with one purpose: to strike an asteroid and measure the effect. Its target was Dimorphos, a small moon orbiting a larger asteroid called Didymos. The spacecraft was no larger than a car, but it traveled millions of miles to meet its target. At the end, it crashed directly into Dimorphos at high speed. Cameras watched as the tiny probe vanished into silence, leaving behind a plume of dust and rock. The result was historic. For the first time, humanity had changed the orbit of a celestial body. Dimorphos's path around Didymos shortened, a measurable, deliberate shift caused by our hand. It was proof that planetary defense was not just theory, but reality. The mission was celebrated worldwide, not because it stopped a threat — Dimorphos was never dangerous — but because it showed we could, if needed. It was humanity's first rehearsal for protecting our home against the silent wanderers of the sky. The DART mission is a reminder of what we can achieve. From fragile creatures bound to one planet, we are learning to reach out, to anticipate, and to safeguard ourselves against the universe itself. What we learned from crashing a probe into Dimorphos. When the DART mission struck Dimorphos, the outcome was more than symbolic. For the first time, humanity tested how much force it would take to change an asteroid's path. And the results surprised even scientists. The impact shifted Dimorphos's orbit around Didymos by more than expected, proving that asteroids are not solid blocks but fragile, responsive worlds. High-resolution images showed plumes of dust and rock streaming into space. Some fragments drifted off into new orbits, others fell back onto the surface. The asteroid had absorbed the strike, yet it also revealed how loosely held together it was. The lesson was profound. If asteroids are rubble piles, then deflecting them may be easier than thought. A single impact can shift far more material than a dense, solid body would allow. But it also means predicting outcomes is more complex. Each asteroid is unique, shaped by billions of years of collisions and fractures. For planetary defense, this was invaluable knowledge. It showed that with enough preparation, a small spacecraft could protect an entire planet. It also showed that asteroid missions are not just experiments. They are rehearsals for safeguarding life itself. What we learned from Dimorphos was not only science, it was reassurance that humanity, fragile though we are, can rise to meet the quiet threats of the cosmos with foresight and courage. The strange, double asteroid systems bound by gravity. Not all asteroids travel alone. Some form pairs bound together by gravity, orbiting each other in a delicate dance. Dimorphos and Didymos are one example, but there are many others. double systems where one larger body carries a smaller companion like a moon. These systems are strange because their orbits are often fragile. The two bodies tug at each other, sometimes exchanging material, sometimes reshaping their own surfaces with the dance of gravity. To see them is to realize that even rocks can find partners in the emptiness of space. Double asteroid systems may form when a fast-spinning asteroid throws off material that coalesces into a moon, or when two bodies collide and remain locked together instead of breaking apart. Each system is a clue to the chaotic history of impacts and creation. From Earth, these pairs appear as faint points of light, but radar and spacecraft reveal their intimacy. Two small worlds circling each other, drifting together around the sun like partners joined in an endless waltz. They remind us that even in silence, companionship is possible. That gravity, the same force that holds us to Earth, also binds wandering stones into relationships across billions of years. Tiny moons orbiting larger asteroids like companions. Beyond double systems, some single asteroids carry small moons of their own. These tiny companions, often only a fraction of a mile across, orbit their parent bodies like miniature satellites. The cosmos is filled with these hidden relationships. Take asteroid Ida, for example. When the Galileo spacecraft flew past in 1993, it discovered a small moon named Dactyl, orbiting it. Until then, no one imagined asteroids could have moons. The discovery reshaped how we view these worlds, showing they can be more complex than simple drifting rocks. These moons often form from debris, fragments ejected by impacts that remain captured in the asteroid's weak gravity. Over time, they settle into stable orbits, circling silently like children around a parent. They may be tiny, but their presence reveals much. By studying their orbits, scientists can measure the mass of the parent asteroid, uncovering secrets about its density and structure. Every moon is not just a companion, but also a key. And so, even in the smallest of places, companionship appears again. A reminder that solitude in the cosmos is rare. Even asteroids, drifting for billions of years, sometimes carry company on their journey. Why some spin so fast they throw off debris. Asteroids are not always steady. Some spin at incredible speeds, completing a rotation in just hours or even minutes. When this happens, their weak gravity can no longer hold on to loose material. Dust, boulders, even fragments of their own surface are flung away into space. This rapid spinning often comes from sunlight itself. The Yarkovsky-O'Keefe-Radzievskii-Paddock effect, or Yorp effect, occurs when uneven heating from sunlight slowly speeds up an asteroid's rotation over time, a force so subtle yet powerful enough to make entire worlds spin apart. Scientists have observed asteroids shedding material this way, creating streams of debris. Sometimes these fragments drift nearby and become moons. Other times they scatter into the solar system, adding to the population of smaller bodies. The thought is eerie, that an asteroid can literally dismantle itself just by spinning too fast. It is a reminder of how delicate balance can be in the cosmos, gravity holding on by the weakest thread while sunlight pulls at the rhythm of motion. Fast-spinning asteroids are unstable, but they also show us how dynamic, how alive even these silent stones can be. They are not dead rocks, but moving, changing bodies, restless under the sun's endless touch, or the rubble pile asteroids barely held together. Some of the strangest asteroids are not solid at all, but rubble piles, loose collections of rock, dust, and fragments clumped together by the faintest gravity. To land on one is to step onto a surface that is more like a floating pile of gravel than a planet. Rubble pile asteroids form when larger bodies break apart in collisions. Instead of scattering into nothing, the fragments drift back together, bound gently by gravity. They look solid from afar, but up close they are fragile, shifting landscapes, ready to crumble at a touch. Bennu, the target of NASA's OSIRIS-REx mission, is one such asteroid. When the spacecraft touched its surface, the probe sank into the dust like a hand into sand, revealing just how loosely packed the material really was. These bodies challenge our understanding of stability. They show that even chaos can endure, that fragments can cling together for billions of years, surviving not because they are strong, but because they are balanced in perfect, fragile harmony. To study rubble piles is to glimpse the delicate side of the universe. Stones that should not have lasted, yet did. Fragile, impermanent, and yet eternal in their drifting silence.